Please make sure that you have put your phones on silent mode, and please take your seats quickly. I request people at the entrance kindly take their seats quickly. Good morning to everyone present here. On behalf of the organizers of the flagship event of IIM-ATM 2025, IIM chapters of Hyderabad, Visakhapatnam, Paloncha, and Nagpur, in association with the Department of Materials Science and Metallurgical Engineering at IIT Hyderabad, I, Dr. Rashmi Singh, warmly welcome you all to the International Conference on Advanced Materials and Critical Minerals for Energy Transition, and to this inaugural ceremony. Andriki Namaskaralu. IIM-ATM Karyakramaniki Swagatam. It is an honor to have distinguished experts, researchers, industry leaders, faculty members, and students with us today as we begin this important three-day event. To begin with the formal proceedings, I request the dignitaries to kindly take their seats on the dais. Professor K. Bhanu Sankar Rao, Convener IIM-ATM 2025, and Professor of Practice, Department of Materials Science and Metallurgical Engineering at IIT Hyderabad. So please take your seat. Okay. Dr. Komal Kapoor, Vice President, the Indian Institute of Metals, and Chairman and Chief Executive, Nuclear Fuel Complex. Dr. Tata Narasimha Rao, Co-Convener, IIM-ATM 2025, and Vice Chancellor of Sri Venkateshwar University, Tirupati. And now, I request Professor B.S. Murthy, President of IIM and Director of IIT Hyderabad, to kindly accompany our chief guest of the day, Shri N. Balaram, CMD, Singareni Collieries Company Limited, Hyderabad, to the dais. Welcome you all. And now I request Professor B.S. Murthy, President of IIM and Director of IIT Hyderabad, to kindly lead them to light the lamp.
भद्रं पश्येमाक्षभिर्यजत्राः स्थिरैरङ्गैः सुष्ठुवागुंसस्तनूभिः विषेम देवहितैर्यदायुः स्वस्ति न इन्द्रो वृद्धश्रवाः स्वस्ति नः पूषा विश्ववेदाः स्वस्ति नस्तार्क्ष्यो अरिष्टनेमिः स्वस्ति नो बृहस्पतिर्दधातु ॐ शान्ति शान्ति शान्तिः ॐ अथ गणे
Thank you, sir. May I now request Professor B.S. Murthy to deliver the welcome address.
Namaste and good morning to everyone, friends here. IIT Hyderabad and Indian Institute of Metals warmly welcome all of you to this exciting event, the 79th annual technical meeting of IIM and the associated international conference that we have today on advanced materials and critical minerals for energy transition. As all of you know, these two terms, the advanced materials and critical minerals, have become a buzzword in recent times, particularly for the country where we would like to establish technologies in India to become what our Prime Minister keeps reminding us, Atmanirbharata, being self-reliant in every one of these areas. So we realize that this is an important topic that we should have it as an international conference for our IIM-ATM this year. All of you know that every year there will be one international conference just before the ATM starts. And this year's conference is going to be on this. I have about 24 experts from all over the world going to give talks today. But what is more important is at IIT Hyderabad, we give so much importance to these two areas that we have now a center of excellence on critical minerals. We have established a research hub with India, Australia research hub on critical minerals, and a large number of programs, including a program on e-waste management, masters in e-waste management is happening. We have a plan to start a masters in critical minerals next year, and a lot of research activity and academic activity is happening in this. We have also felt that every advanced materials needs a lot of characterization facilities. At IIT Hyderabad, we have recently set up with about 80 crores, which means around 10 million US dollars, what we call it as in situ and correlative microscopy center. We would like to see that all of you sitting here, whoever needs high-end microscopy, this is a place where we would like to make it as a single spot for all of you to come and do anything in situ microscopy. While microscopes exist everywhere, this is the first center in India on in situ and correlative microscopy, and any such deep knowledge about materials that you would like to gain and improve the research capabilities of all of us, I think this particular center would be of great help to all of you. So these are all important in the advanced materials area, and understanding the materials at the depth so that you can create and design new materials. And the whole objective of this particular conference is to understand better how do we design new materials and ensure that the right kind of components with these materials are brought out, and see that India not only becomes Atmanirbhar, the self-reliant, but also another slogan that our Honorable Prime Minister keeps reminding us is what we call it as Viksit Bharat, India becoming a developed country in the area of advanced materials and devices. So with that few words, once again, welcome you to this beautiful campus of IIT Hyderabad. I'm sure as you walk around, you see a beautiful campus. You have 3 days. You are going to be here. I request you to explore, and more importantly, explore collaborations. I'm a strong believer that collaborations are key to growth, and I'm sure working together, we can do much greater things. Bringing people together will bring synergy so that 1 + 1 can be significantly greater than 2. With those few words, thank you very much for being here with all of us.
Thank you very much, sir, for a very warm, extremely informative, and motivating welcome address. I now invite Dr. Tata Narasimha Rao to share his introductory remarks.
Good morning, everyone, and respectable dignitaries on the dais, off the dais, students, friends, ladies and gentlemen, my colleagues. Uh, it's a great day. Although I am a material scientist, I can see a lot of metallurgy people here, and the conference is on materials and metallurgy. And then I have been given the responsibility of getting people for the first day conference, that is 2-day parallel sessions, one on advanced materials and another on critical minerals. And then as our president, Sri Professor Murthy said, that the importance of the present day for both areas is need of the day. And I see a lot of industry representatives, academicians, and experts in these two areas. And then we have designed the program in such a way that it caters to all materials and metallurgy people and critical minerals equally. So please don't miss all these sessions. And then I also request all the people, I'm now representing Andhra Pradesh also as Vice Chancellor. Recently I took over as Sri Venkateswara University. And then Andhra Pradesh has got a lot of mineral resources, especially in the coastal belt. And then we want to start with the help of Mohanji and then our President, a new course on metallurgy and metals, because we need critical manpower to address these issues in the future. So I hope this will be a great successful event, and thank you very much for all of you coming, and then enjoy the program. Thank you.
Thank you very much, sir. Now I invite Professor Pinaki Bhattacharjee, Professor from the Department of Materials Science and Metallurgical Engineering, IIT Hyderabad, to provide a brief overview on the advanced materials. Welcome.
I think a very good morning to all the very eminent speakers from different parts of the world, and all the delegates, and all the students who are joining this today conference. So I think just a few minutes back, I have been requested to talk about the importance of advanced materials. And it is rather very difficult to talk about advanced materials, particularly after Professor Murthy, because he has not left any room to speak more. Okay. But if we look at the program, we can talk about there are basically two parallel tracks, one on the advanced materials and one on critical minerals. Now, there has been a thought process between the linkages of these two parallel tracks. What we believe is that advanced materials requires your critical minerals and metals, and similarly critical minerals and metals should exist because for their requirement in the advanced materials. So these are not two separate, but very, very integrated tracks. And if you look at the advanced materials program that we have developed for this, we have, from the session, we have a classical alloy design and development, and a lot of the talks are related to basically more emerging materials like high entropy alloys, their properties, and their possible applications, technological applications in the future. And then energy materials like batteries, solar cell, photovoltaics, and we are all aware about their importance in the energy landscape of the country. And then we have a session on processing and applications of novel alloys, where we will talk about more established materials like steels or oxide dispersion strengthened alloys for high temperature applications. So they are extremely industrially relevant, but there are a lot of developments are going in that front also. And finally, we come to the session on quantum and electromaterials devices, and there have been a lot of talks which are going on in the quantum sciences and quantum devices, so this is one of the very, very emerging areas. So you can see that the whole program has developed to address the various facets of the advanced materials, and I am sure that all of you who are attending this program will be greatly benefited, particularly the students. I would request them to attend all the talks, so the knowledge, or more importantly, the inspiration that you take from here will guide you in your future. Thank you very much.
Thank you very much, sir. Next, may I request Professor Narasimha from the Department of Chemical Engineering, IIT Hyderabad, to share his insights on the critical minerals. Welcome, sir.
Good morning, ladies and gentlemen, and respectable dignitaries on the dais, of the dais. Welcome for the international conference on advanced materials and critical minerals. I'm particularly coordinating with respect to critical minerals. Now, I believe, is a need of the time for the nation to look at on the critical minerals, ranging from resources, starting from primary, secondary, as well as tertiary. Then we have another session followed with respect to physical beneficiation and the beneficiation for the critical minerals to the maximum extent of the grade that we can able to do. And followed by third session, we have specifically for refining. And particularly after mineral beneficiation, what we see is we have to enrich them to the level where we can think of a maximum extendable recovery and refining through hydro and pyrometallurgical routes. And the last session, which also spans into recycling, because now the immediate action that India we can really rely upon to get our critical metals recovering effectively. So I think the 4 sessions have about a total 12 plenary speakers, and 6 from overseas and 6 from in India. And I believe the way each plenary talk is being aimed to get the best out of their expertise, both in overseas as well as India, so that we can able to really see what is happening on a critical minerals around the globe. And then I believe most of you as audience, you would enjoy the technical merit of this international conference first day on critical minerals sessions. Thank you.
Thank you very much, sir. I now invite Dr. Komal Kapoor, Vice President, IIM, to address the gathering.
Dignitaries on the dais, Mr. Balram, the chief guest of today's inaugural symposium, Dr. B.S. Murthy, the President of Indian Institute of Metals, the other dignitaries, the Vice Presidents, the past Presidents, industry sponsors, participants from laboratories, research institutes, academia, and the delegates. Well, it's a pleasure to, come here and then inaugurate this first one-day event, which is the event on symposium on advanced materials and critical materials. Well, it's a very, very intense program today with talking about the critical minerals, the resources, the processing, the recovery, and then talking about advanced materials, the materials which are used in the most important sectors, materials which are highly desirable for the sectors of space, defense, and nuclear. Friends, the critical minerals, as you know, presently they are the currency of a country. They dictate the economy of the country. It's such an important aspect of today's world that the availability of critical minerals, the availability of technologies to process advanced materials is determining the growth of the country. So it's very, very important for us, all of us who are from different organizations, different institutes, to come and recognize the importance of these materials. And then Indian Institute of Metals, which is the gold bearer of such a taking topic as a topic for today's conference. And I must say that this kind of venue, which is an academic institute where the talents are nurtured, is very much required to sensitize the need of these materials presently in the country. I thank the organizers who have made a great effort in organizing this event, and I welcome you all. Thank you very much.
Thank you very much, sir, for a very inspiring address, especially to the young ones. It is now my pleasure to invite Shri N. Balaram, CMD, SCCL, to deliver the chief guest address for this inaugural ceremony. Shri N. Balaram is CMD, as I said, of Singareni Collieries Company Limited, and he's well known for progressive leadership focused on sustainable mining, worker welfare, green initiatives including afforestation and solar power, technology adoption and diversification into critical minerals. He is a senior IRS officer and has received several awards, including Tree Man of India and Best CMD Award. Sir, I welcome you.
Good morning, all. Respected Dayas, Professor B.S. Murthy Garu, President IIM, Professor Bhanu Shankar Rao Garu, Dr. Komal Kapoor Saab, Vice President IIM, Dr. Tata Narsingh Rao Garu, and of the Dayas, CMDs, directors, and senior professors, doctors, scientists, and all stalwarts. I am odd man out. I am not an engineer. I am not an engineer. I am from arts background. And to say a few words, I wanted to become an engineer, but I could not. But I am leading a company of an engineer-dominant company, that is Singareni Collieries Company Limited, which is into coal production, thermal power generation, solar, other hydro and carbon related initiatives. So I am thankful to Dr. B.S. Murthy Sir, who is a dynamic leader, scholar, academician, and he is the forefront in conducting and paving way for India to head in technology advancement with these conferences and collaborations. It is my privilege to join you today at inauguration of IIM-ATM 2025 and a prestigious international conference on advanced materials and critical minerals for energy transition. As the world accelerates toward a low carbon future, one fact has become increasingly clear: critical minerals are the new oil. They form the backbone of solar panels, wind turbines, EV batteries, green hydrogen systems, power transmission networks, and advanced material technologies, defense, and other critical sectors. The globe race for mineral security and supply chain resilience has rarely been more intense or more important. In achieving a green energy transition and realizing the vision of Atmanirbhar Bharat, critical minerals plays a crucial role. Ministry of Mines has finalized various minerals as critical and strategic, which is need of the hour. Their secure supply now defines national preparedness, industrial competitiveness, and technological self-reliance. And we are all aware, Government of India announced the National Critical Mineral Mission, in which around 18,000 crores of rupees to invest from the private sectors and public sector. Apart from that, to move the step forward and to accelerate the Government of India's mission for the critical minerals, and the Government of India is further thinking to give the loans from NMET, National Mineral Exploration Trust, at low interest or without interest And given the critical role of the rare earth elements in driving clean energy technologies, the availability of this data presents a valuable opportunity to tap into a domestic underutilized resource. Recognizing potential of this resource, Singareni College Company Limited decided to conduct a comprehensive scan of clay, shale, layers associated with the coal seams in all open cast mines. A state-of-art geoscience laboratory will be established in Singareni. China has banned the export of the both raw materials of different, you are aware. For a country like India, developing strong capabilities in exploration, processing, recycling, and material science is not just an economic opportunity, but a strategic necessity. As Albert Einstein quoted, I am thankful to all those who said no to me. It is because of them I am doing it myself. In light of the circumstances, SCCL has pinpointed the crucial steps involved in extracting rare earth metals from clay, shale, processed OB, and bottom ash and coal. This endeavor necessitates collaborative synergies between industry stakeholders, research laboratories, technological experts, processing engineers, and academic institutions. Bridging the gap between diverse professional domains poses a formidable challenge. Nonetheless, we are resolute in our pursuit to achieve harmony, or at very least a workable compromise. Hence, we have proceeded to assess the capabilities of various Indian agencies that could provide collaborative support and expertise, potentially partnering with ACCL in its rare earth metal extraction endeavors. And we have entered MOU with IIT Hyderabad, Institute of Minerals and Material Technology, CSIR MMT Bhubaneswar, and Non-Ferrous Material Technology Development Center, NFTDC Hyderabad, to achieve its goal, rare earth metal extraction from its feedstock. And in feedstock, we have found different rare earth elements, and the ppms varying from 50 to 650 for different, that's scandium, strontium, vanadium, niobium, lithium. Apart from the exploring these possibilities of extracting REEs from clay, a detailed study was conducted on the clay samples. And we have also become a part of Kabil, Khanij Videsh India Limited, and Ministry of Mines, the secretaries earlier Kantarao Garu and Piyush Goyal, they have recognized Singareni's contribution, or our partnering, or trying for to do a little bit from the company. And in recently, they made Singareni College CMD as a member in National Strategic and Critical Minerals, which is appointed by Niti Aayog. So SCCL management has decided to establish a pithead entry-level demo commercial plant at Satupalli open cast. By adopting this approach, we aim to venture into RE exploration and exploitation up to TRL 8 and TRL 9, potentially unlocking new revenue streams and enhancing resource utilization in our open cast mines. As an offshoot, the SCCL also proposes to develop a standard certified reference center for the clay fly ash apt to Indian scenario for the benefit of the agencies in the estimation of the REs in the fly ash and clay material. I would like to take a moment to express my sincere appreciation for the invaluable contributions your esteemed institution has made to the field of research and development. Your institution's commitment to advancing the knowledge and innovation has been truly commendable, and we are grateful for the impact it has on our industry. We are looking forward to work with IIT Hyderabad and today's all the guests and stalwarts and leaders of industries and academicians in fulfilling India's vision of Atmanirbhar Bharat. Jai Hind.
Thank you very much, sir. I now request our chief guest to release the conference souvenir of IIM 2025. I request Professor Murthy to accompany him and all the dignitaries to kindly participate. Thank you very much, everyone. Now I request President IIM, Professor Murthy, to present the memento to the chief guest of today. Thank you very much, sir, and we look forward to continued collaboration between SCCL and IIT Hyderabad in future too. I now request Professor K. Bhanu Sankar Rao, convener of IIM-ATM 2025, to deliver the vote of thanks.
It gives me immense pleasure to extend a very warm welcome and greetings to all the participants, former presidents of IIM, esteemed guests, students, and sponsors of the technical exhibition. On behalf of the organizing committee of the 79th Annual Technical Meeting of the Indian Institute of Metals and the International Conference on Advanced Materials and Critical Minerals for Energy Transition. The International Conference is designed to bring internationally known experts from academic, industry, and research institutions to discuss the status and emerging challenges and opportunities in employing and tailoring advanced materials and critical minerals for energy transition by fostering robust scholarly dialogue and cross-disciplinary engagement. In the international conference, we have 24 invited plenary speakers from Australia, Japan, France, USA, Germany, South Africa, and India. President of IIM has taken very keen interest and made meticulous planning in knitting the topics of international conference. He has been very critical in reviewing each and every aspect of the conference and guided the very young team associated with IIM-ATM 2025 in achieving perfection in its organization. Without his deep involvement, this mammoth conference would not have been taken its current shape. I would like to thank him for all his sincere efforts for making IIM-ATM 2025 as a memorable, massive event in the annals of IIM. This event serves as a dynamic platform to foster collaboration and knowledge sharing among leading industry experts, researchers, academicians, and thought leaders. The discussion and insights gained during these sessions will not only contribute to overcoming current technical hurdles, but also help to shape the future of advanced materials and critical minerals for energy transition. Balram Garu introduced himself. He is not an engineer, but you have listened to him, and his speech is what I can say, light-bearing for this conference. I thank him for taking valuable time and coming over in spite of having busy schedule. To tell you frankly, he has to meet some ministers today from Rajasthan. But in spite of it, he has made this event. I would like to thank you, sir, for your particular this one. I will be failing in my duty if I am not thanking all my colleagues who have been working tirelessly for the last 1 year to make this event a grand success. Thank you very much. I would request all of you to enjoy the sessions and pass on your inputs for future activities that are to be taken on advanced materials and critical minerals. Thank you very much.
Thank you very much, sir. It is indeed delightful to host this excellent gathering and to have our chief guest with us today at IIT Hyderabad. One more time, welcome you all. We will now proceed to the inauguration of technical exhibition of the IIM-ATM 2025. I request the dignitaries to kindly proceed towards the exhibition area for the formal inauguration of the technical exhibition. I also request the audience to remain seated during this time. The first technical session will begin at 10:05. I request all the participants and attendees to be present in their respective halls. With this, I request the dignitaries to kindly proceed towards the exhibition. Thank you very much for gracing the event today. Another announcement, the technical exhibitions will remain open for all 3 days of the conference. You're welcome to explore the stalls at your own convenience throughout the event. Thank you very much. There's one more announcement that registrations for the conference will also be open for all 3 days. Thank you.
Hello, hello. Hello. Uh, just an announcement. We are going to start the next technical session uh, on the advanced materials at this very hall, lecture hall 5. And the critical minerals resources will take place in lecture hall number 6, which is just opposite to this lecture hall 5. Again, I'm repeating, the advanced materials session will take place here at 10:05 a.m. and the critical minerals will take place in lecture hall number 6, which is opposite to this very hall. Thank you.
Hello everyone. I request everyone to please be seated. The session will start in less than 5 minutes, please. Hello everyone. Please be seated. I request the chair of the session 1, Professor Pinaki Bhattacharya, to take his seat.
So let me welcome you all again in the advanced materials track. So this is the inaugural session, and I request you to please enjoy the session. So in this session, we will have basically 3 talks from 3 very eminent and distinguished speakers. And our first talk of this session is going to be by Professor S.O. George from Oak Ridge National Laboratory. And his topic of presentation is deformation phenomena in high entropy alloys. So welcome, Professor George. Okay, yeah.
Yeah. This is forward, backward. Yeah. So thank you very much. I want to thank the organizers for this opportunity to talk about high entropy alloys. My background is mechanical behavior, so I'm going to talk about applications or potential applications of high entropy alloys for structural purposes. As many of you probably know, there are now there's more and more interest in high entropy alloys for functional applications, but that's not my area, so I'm going to talk about deformation phenomena in high entropy alloys. There may be some in the audience who have not kept up with the literature on high entropy alloys, so especially for the younger people, the students in the audience, I'm going to talk, I'll give a little background on high entropy alloys. It's a fairly new area, so the first paper appeared in 2004 by Professor Ye and colleagues in Taiwan. And this was published in this journal here, Advanced Engineering Materials. And this field now has grown dramatically. This is not the latest information, but a few years back, I looked up Web of Science to see how the number of papers and the number of citations in the general area of high entropy alloys was increasing as a function of time. And starting about in 2013-14 is when the field took off. So the first 10 years, it was going along fairly at a low level, and then starting about 10 years ago, it took off really dramatically. So when you look at high entropy alloy and compare high entropy alloys with conventional alloys, one way to think about it is if you have a simple ternary system with A, B, and C at the corners of the ternary, then if you consider this corner just as an example, the B-rich corner, then the conventional alloys are typically in this corner here. So they're rich in one element, and to which small amounts of other elements are added in relatively small concentrations. So you have primary element, which is a solvent, as we all know what solvents are, and then the secondary elements are solutes. Don't see the anyway, and so the secondary elements, is this pointer not working? Oh, that's okay, don't worry. So at this corner here are the conventional alloys, and then in the middle of the phase diagram, and you can imagine that you have a quaternary system, so instead of a triangle, it will be a tetrahedron. But at the center is this vast region that's shown in red that is largely unexplored. And if you think about being exactly in the middle of that triangle, then you have equal atomic concentrations of A, B, and C. So it's 1/3, 1/3, 1/3. If it's a quaternary system, it'll be quarter, 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 and so on. And this region in the center is largely unexplored because there are millions of compositions that are possible. The number of combinations explode dramatically when you have more and more elements. So when you have 4 elements, 5 elements, and so on, the numbers get very large soon. And so that's why it hasn't been explored very much. And so the hope, and it hasn't been realized yet, but the hope is that among these millions of possibilities, maybe there are 1 or 2 that will be in there that are useful. So that's the driving force for why we're interested in this. And of course, as any new area that sort of rises in popularity soon, there's a lot of papers published. And of course, as a result of this, there are a lot of claims. Some of it has merit, and some of it doesn't. And I've listed a few of these claims that have been made over the years of high entropy alloys. And the founding claim, or the founding hypothesis in that Ye paper that I mentioned, was that configurational entropy stabilizes solid solutions. The argument is that when you have opposing enthalpy of formation of compounds, intermetallic compounds, and you have entropy which wants to disorder everything, then at some point, if the entropy term is very high compared to the enthalpy term, then it will dominate, and you will get a solid solution, which went against all metallurgical intuition, because as metallurgists, we always want to stay away from the middle of the phase diagram, because that's where all the intermetallic compounds form. We want to stay at the ends of the phase diagram. And so this was kind of a revolutionary hypothesis at that point. Unfortunately, it turns out not to be true. And so I will show you a very simple experiment that very clearly demonstrates that is not the case. The other claim that's been made is that when you have multiple elements in an alloy, then because of the interference of the different elements, then it will result in sluggish diffusion, right? And this concept is questionable at best. It's wrong in many cases, and I refer you to Sergei Divinsky's talk, who will talk later in this session, and he'll go into much more detail. And I think he will show that there is no sort of uniform statement that you can make about sluggish diffusion. But I will leave it to Sergei to talk about that. The other point that was made is that if you have solutes added into a solid solution, one solute increases the strength by a little bit, and you have two solutes, it'll be better than one solute, and 3 will be better than 2, and 4 will be better than 3, and so on. And so the idea was that the greater the number of the solutes, the higher the strength. And again, this is not true. I'll show you a couple of examples. Now, in the last 2 or 3 years, a claim is being made that short-range order is somehow special in high-entropy alloys. Short-range order has a long history. It's 50-plus years old. In simple systems, it's been well studied. And we know some of the benefits and some of the disadvantages of short-range order. But somehow, in the case of high-entropy alloys, there's this claim being made that short-range order is fundamentally different and responsible for all these magical properties in high-entropy alloys. And I will show you that that is also not quite true. And finally, there was a lot of excitement that refractory high-entropy alloys, in which the component elements are refractory elements, might be able to replace superalloys in the future. And I leave that with a maybe question mark, right? And the reason is these are very, very difficult materials to process. There's very little data available on them. Practically no tensile properties, a few compression data points, practically no creep data. We have one of the few creep studies. I will talk about that. And the answer to this question is still unknown. So there's a lot of research that needs to be done on whether these will be viable high-temperature materials. Okay, so having said that, so I don't want to leave the audience with the view that there's no hope. We think there are interesting niche applications where high-entropy alloys will fill a void. At cryogenic temperatures, I will show here in a minute, some of the face-centered cubic HEAs are outstanding. They have exceptional properties, better than anything else that can compete against them. So for cryogenic applications for deep space, if you want to do construction on Mars, if you want to build things in the Arctic, they have some remarkable properties. Of course, cost is a criterion, and we have to figure out how to make high-entropy alloys with cheaper constituent elements. At elevated temperatures, precipitation hardening of these refractory high-entropy alloys shows some promise, but there's a lot of work that needs to be done, and I'll talk a little bit about that. And of course, they all have oxidation problems. So let me talk a little bit about what the cryogenic properties are and why they're so exciting. So there are some solid solutions in the high-entropy alloy space that appear to be stabilized by entropy. So this chrome, manganese, iron, cobalt, nickel, which is commonly referred to as the Cantor alloy, was the first one to show the solid solution stability. And you can see over a range of length scales, all the way from SEM level, EBSD, TEM to atom probe, it can be stabilized as a single phase. And it doesn't take huge effort to quench in the solid solution state at room temperature and maintain the solid solution state. So we were surprised that for 10 years or so after the birth of the field, people just took it at face value that entropy stabilizes solid solutions, and nobody had actually tested this hypothesis. Is it really true that higher the entropy, the more stable the solid solution. And so we decided to do a very simple experiment. So you could keep adding more and more elements to an alloy and see whether the solid solution stability increases, or you could take an alloy that was already known to be a solid solution, and if it had 5 elements, you could take one of the 5 elements and throw it away and replace it with another element. And the configurational entropy is constant, right? Because you still have 5 elements, and so the entropy has not changed. You've just replaced element A with element B. And now you can go and replace this other element X with element Y, and so on, and systematically, one by one, replace each element in this 5-component alloy. And to give it the best chance that these new alloys would also be single-phase solid solutions, we tried to use Hume-Rothery principles to make sure that their atomic size misfit was similar, their electronegativity, the Pauling exclusion, electronegativities were similar, the valences were similar. So all the rules, the Hume-Rothery rules, we try to satisfy as much as possible. And so, for example, on the right top, you'll see that we replaced chromium with vanadium. So we replace only one element at a time, so the entropy doesn't change. And we replace BCC elements with BCC elements, and so on and so forth. And so we made up all these different alloys, and we looked at what the microstructure looks like. And to our surprise, not a single one of these new alloys is a single-phase alloy. So everything is multi-phase. So clearly, solid solution stability is not a direct function of entropy, because if it was, all these, since they all have the same entropy, they would all be single-phase solid solution. And some of them are so brittle, you can see the microstructure, or the photo in the middle there, where the casting just broke into pieces right away. Okay, so it's really not entropy stable, and there'll be a lot of studies after this which confirm the fact that entropy is not a controlling feature here. And so Thomas Huxley, you probably know his brother Aldous Huxley, who's a famous writer, but this is his brother, who was a biologist, and so he said the great tragedy of science is that you can have a beautiful hypothesis, but it can be killed by a very ugly fact, right? So in the end, the fact is what matters, doesn't matter. And as Feynman said, it doesn't matter how beautiful your theory is, it doesn't matter how important the man is who's making the hypothesis, it doesn't matter how famous you are. In the end, if the experiment doesn't agree with the theory is wrong, right? And so I think the entropy hypothesis is just wrong. Okay, so that doesn't mean that these complex alloys are not useful. So here's an example of the Cantor alloy that shows fairly dramatic increases in strength and ductility as you decrease the temperature. So if you look at the middle plot, which is the strength versus temperature, what you find is that as you decrease the temperatures, the strength increases. Now remember, this is an FCC system, right? So this is what, if you didn't know what the system was, you would think it was a BCC alloy, because BCC alloys show this dramatic increase in strength because of the piles hardening at low temperature. But BCC alloys will also show a ductile-brittle transition. So as you decrease the temperature, the material would get really brittle. But if you look at the plot on the right side, which is the tensile elongation, the elongation increases at the same time as the strength increases. So, which is kind of an unusual phenomenon in material science, because we're all taught that strength and ductility go in opposite directions. So you get this very interesting increase in strength and ductility that go hand in hand, and they increase as the temperature decreases. And not surprisingly, because of this, when strength and ductility increases, then I'll show you in a minute that toughness increases too. The reason why strength increases with decreasing temperature is that necking instability, which is the Considera criteria that we all know, the considered criteria says that when the strain hardening cannot keep up with the decrease in the cross-section of your sample, then the material necks, and once it necks, then it's all over, because then all the subsequent deformation is localized in the necked region, right? So you want to postpone necking as far as possible, and the figure on the right shows the plot, which is that necking criterion, which is the considered criterion, which is the strain rate should be at least equal to the strain, the true strain. So that dashed line on that last plot there is, sorry, the pointer doesn't work. Anyway, so the last line, that dashed line there is where the equation d sigma d epsilon is equal to sigma. So everything to the bottom of that is where necking takes place, and everything at the top of that is where necking does not take place. And you can see as you decrease the temperature, the point at which necking occurs shifts to the right. And you can see from the fracture surface that as you decrease the temperature, necking is suppressed too. Okay, so then we decided, okay, let's take a look at all these subsets. So you can take the 5-component Cantor alloy and make all equiatomic subsets that no. Okay. Okay. So you take this 5-component alloy and you make all the quaternary subsets and the ternary subsets and the binary ones and so on. And then we identified everything that was a single-phase FCC system. And that's shown in red here. And just to give you an idea of the scale, this is what pure nickel behaves like, right? So it's almost temperature independent, it's yield strength. And this is what the 5-component alloy behaves like. So this is why I said it behaves more like a BCC metal than an FCC metal. Most FCC metals are flat down in this region. And so this is nickel at this end, and this is the 5-component alloy at that end. And so we decided to look at everything in between. And when you do that, what you find is that that entropy does not really scale with strength. So the strongest and the most ductile alloy is the 3-component alloy. The 5-component alloy is sort of the fourth from the top. So clearly, the hypothesis that entropy, increasing the entropy increases the strength and ductility is not valid. And there are lots of experiments that have confirmed this since then. And as a result of all this, you can find that the 3-component alloy, the chrome cobalt nickel, which is the strongest and the most ductile alloy, has actually quite exceptional fracture toughness behavior. So at liquid hydrogen temperature, 20 Kelvin, it has fracture toughnesses that exceed 500 MPa root meters. So numbers that have not been seen in any other material before. And so it's really one of the toughest materials known to man. So it's up here, this region up here, compared to all the other material systems. So what's the underlying mechanism for this dramatic increase in strength and ductility as you decrease the temperature? So what I've plotted here is the strain rate, so d sigma d epsilon, but I've normalized it with respect to the shear modulus. Because if you don't, shear modulus is temperature dependent, right? So if you don't normalize with respect to shear modulus, these two curves would be separated. And so to collapse them onto the same curve, you normalize with the shear modulus. That gets rid of the shear modulus effect because the shear modulus at 77K is higher than the shear modulus at room temperature. So when you normalize, they fall on the same curve. And if the only mechanism of strain hardening was Taylor hardening, dislocation interactions, then both these curves should fall right on top of each other, right? Because the Taylor hardening, especially once you normalize with respect to the shear modulus, should fall exactly on the same curve. But somewhere around 10% strain, these two curves diverge, right? And so what is the reason for this divergence? And it's because something else, some other mechanism is occurring at that 10% strain. So if it was only dislocations, right? So you can see that this is the strain hardening due to dislocation. It goes as square root of, this is a Taylor model, it goes as square root of dislocation density. So if you normalize this by G, so you take G over onto the left-hand side, and Berger's vector B is a constant, the only thing that would make a difference is the dislocation density. So we measure the dislocation density as a function of temperature for different strains, and we find that there's no difference between 77K and room temperature. So this by itself cannot explain this divergence. So there must be some other mechanism there. And the mechanism is twinning. So twinning starts occurring almost exactly at 10% strain. So this is about 10% strain. So if you interrupt specimens before at 1 and 2, you see mostly dislocation behavior. And then you start to see the first hints of twinning at around 2. And then by 3, then you see twins everywhere, right? So somewhere between 2 and 3, which is around where we see this divergence, is where twinning starts as a mechanism. So the other point that I want to talk about quickly is the short range order that people. This has been a big fashionable topic for the last 2 or 3 years. But in these transition metals, chrome, cobalt, nickel, for example, the scattering factors, the atomic scattering factors are almost identical. So it's very difficult to identify from diffraction whether you do have short-range order or not. So a lot of what people have claimed as short-range order, we think are artifacts. And so we very carefully with Professor Inouye at Kyoto University, he and his colleagues have shown very clearly that short-range order cannot be detected by diffraction techniques because the atomic scattering factors are so close to each other. But you can indirectly measure short-range order by resistivity measurements. So if you do resistivity measurements, what you find is that depending on the temperature, so if you take, say, 773 Kelvin, so you see very low resistivity at low temperatures, and then the resistivity increases because you start to see more and more short-range order. And there's a time temperature dependence, right? So you need enough kinetics to move the atoms around to get short-range order, but and for which you need temperature, but if you raise the temperature too much, then the short-range order goes away because the entropy tends to dominate. And so at very high temperatures like 973 Kelvin, you don't get much short-range order, the green one. At very low temperatures, you don't get short-range order because the kinetics are not fast enough. And then you get, in between, you get different amounts of short-range order. So the fact that short-range order exists is not surprising. You see it in binary systems, so it's not surprising that you'll see it in ternary systems. The question, though, is, yes, you do have short-range order, but does that actually have any effect on mechanical properties? And the answer is no. So there are all these papers out there where people have done, I think, incorrect experiments where they claim that short-range order has all these magical effects on yield strength. But what we find is that at both at room temperature and at 77 Kelvin, the short-range order is essentially independent. It has no effect on mechanical properties. So this is as a function of annealing temperature, and this is as a function of annealing time, and you can see in both cases it's flat within experimental error. So I want to quickly now point to another mechanism where, in addition to twinning, you can have phase transformations that can generate can generate interfaces and can generate strain hardening. So if you do a thought experiment and you say, okay, I take a composition, and in one case, I select a composition using a CalFad such that when you quench it at when you take it to high temperatures, it's fully FCC austenite, and then when you quench it down to room temperature, the austenite transforms to martensite. And in this case, we selected a martensite that was cubic, body-centered cubic martensite, not a tetragonal martensite that you would see in steels. So that's this one over here, where your austenite at high temperatures, your martensite at low temperature. Now you take this exact same composition and you put in, let's say, inert obstacles inside. So imagine that you just put rocks inside, right? So these are precipitates, and they're inert. And now you do the same experiment, and if you control the size and the spacing and the distribution of these rocks, they would constrain the phase transformation, and you would suppress this martensitic transformation in this case. At least that's our thought experiment. And you would suppress this. Now you take this metastable FCC at room temperature and you deform it, and now you are able to give it the energy to overcome the activation barrier, and you might be able to get stress-induced phase transformations. And that's in fact what we see. So if you have no precipitates, essentially you see nothing but BCC martensite. When you have precipitates, you see metastable FCC, which is the red one. I mean, it's not 100%. You get a little bit of BCC that still transforms, but the bulk of it is FCC. So this is metastable FCC, and that's there because of all these precipitates that are making it difficult for the martensite to form, right? And you can do diffraction experiments and so on to confirm that. And this then reflects in the stress strain behavior. So the black curve is the curve for this BCC, right? So the BCC doesn't work harden at all because there's no mechanism for work hardening, but the metastable FCC work hardens like crazy. You can see the huge amount of increase in strength and as a result ductility. This one necks almost immediately after yielding, and here you get all this work hardening. And this is due to this FCC progressively transforming under deformation into martensite. And so you can see that in the initial case, this is neutron diffraction. Initial case, it's all FCC. After about 2% strain, you start to see the first hints of BCC forming, and then after about 8% strain, you see lots of BCC forming. So progressively, as you strain it, you get strain hardening due to stress-induced martensite. So at very high temperatures, this is the final part of my talk. At very high temperatures, the current materials are limited to around 1,000 or 1,100 C. So if you want to go beyond that, we are kind of, with existing nickel-based superalloys, we're kind of at the limit of where we might be able to how much more we can increase the operating temperature. So Zenkov and co-workers found this alloy, which is titanium, zirconium, niobium, tantalum, hafnium, and they were able to get it to cold roll and get tensile ductility. So we made some large ingots of this at Oak Ridge. So this is what the casting looks like, and then we were able to roll it into large sheets and get, and then you recrystallize it and you get nice microstructures, single phase BCC microstructures. And they're random, pretty much randomly oriented, very little texture, so which is good. But now the bad news. So if you take this refractory high entropy alloy and you compare it to the creep behavior of let's say single crystal CMSX4, which is one of the state-of-the-art nickel-based superalloy. So this is CMSX4 at around 1100 C. This is CMSX4 about 1000 C. So very, very high stress is needed to reach a strain rate of about 10 to the minus 7. So if you just look at this horizontal dotted line. And if you compare that to this refractory high entropy alloys, so that's what the refractory high entropy alloys look like. So orders of magnitude weaker than the CMSX4. Okay, but that's not so surprising because CMSX4 is a two-phase gamma-gamma prime alloy. So what happens if you take the gamma prime out and you test just the matrix of CMSX4? And that's this one over here. This is a single crystal matrix of CMSX4, and it's still weaker, quite a bit weaker than the matrix of CMSX4 at around 1100 C. And the reason I think is because the matrix of CMSX4 is FCC, which the diffusion rates are much slower, and here the matrix BCC diffusion is much faster. So what you need to do then is to take this material and find suitable precipitates that can potentially strengthen it. There's a lot of work going in this area. Right now, I'm not going to further details because there's very little to report on the effects of precipitation hardening, and we'll see in the next 5 years whether they result in better properties. Okay, so to summarize then, the FCC alloys have great potential at cryogenic temperatures, but the cost of these existing alloys, because they contain chromium and cobalt and nickel, it's quite expensive for structural applications. You need something that's cheaper. So ideally, you want something that's iron-based, that has the same kind of mechanistic processes that are going on, and which will give you the same cryogenic properties. For the BCC HEAs, a lot of additional work still needs to be done. It's very clear that single-phase BCC HEAs just will not cut it. They're too weak, so you need precipitation hardening. The problem is finding the right precipitates that are stable, and that's just from the mechanical property standpoint. And then there's this whole other business of oxidation resistance that's also pretty hard to overcome. So with that, I will stop and take some questions. Thank you.
So thanks, Professor George, for your very interesting talk. So this talk is now open for discussion. So if you have any questions or comments. Yeah. Okay. We'll go ahead with him. Yeah.
Very interesting talk. Thank you very much. I just go back to the initial part of the presentation. First we're supposed to announce who I'm Dr. C.G. Krishnadas Nair, former chairman of Hindustan Aeronautics and one of the past presidents. I've been hearing about high entropy alloys for several years and also seeing some of the papers, but I want to, you told me your specifically talk is on deformation, but question is about what is the level of development? Has it entered any industrial application? One, just a follow-on question, then I'll stop. You can answer both together. Another one, you mentioned the high potential for these alloys, which are towards ceramic type, could be replacement for the nickel-based superalloys. Now, you know, all over the world, engine designers are looking at higher turbine temperatures going up to beyond 2000, even if possible 2500 and so on, where nickel-based alloys or any superalloys so far made is not possible. They are looking at refractories. But now if there is an opportunity, why, if there is any work being done in this field, intensive work, because I'm sure many industries, including from India perhaps, will be interested in applications and funding. Definitely GE and Rolls-Royce, Safran may be having programs to fund if there is somebody to work on it. Can you comment on this? Thank you.
Yeah, so let me start with the refractories first. On the refractory high entropy alloys, my personal view is that right now there may be applications where the exposure times are limited, right? So for example, in rockets and engines, or things that last minutes rather than hours or years, right? Because for something to last thousands of hours in an aircraft engine, you need oxidation resistance, which these things don't have. But there are things where the lifetime in a rocket may be only 3 minutes or 5 minutes or whatever, right? And in which case, there may be a room for some of these refractories. But the question is, how do these complex refractory high entropy alloys compete against traditional refractories, which are simple and which exist? There are commercial versions of tantalum alloys, of niobium alloys, and so on, as you know. And so we're in the process of trying to evaluate this right now to see whether there's any real advantage. Forget about oxidation and all the long-term creep aspects, but just even in quasi-static applications, are there any true advantages of refractory high-entropy alloys compared to traditional, conventional, simple refractories at, say, 1500 C or higher, right? And if there aren't any advantages, then I don't think there'll be industrial interest because there are existing alloys. Right? So that's where I think the refractories stand. On the earlier part of my talk, the FCC alloys, I think if there is an opportunity, it is at cryogenic temperatures, so in very cold applications, because they have very superior fracture toughness properties that nothing else has. But as I said, cost is a major criterion, so you have to figure out whether there are some special applications where cost doesn't matter, and in which case these alloys will work. Otherwise, some new alloys like iron-based alloys will have to be developed in that case.
Okay.
Yeah.
Okay. Thank you, Professor George. I really excuse because we are running a bit late, so we can only take one question, Professor George. So,
yeah, thank you, Professor, for such an insightful talk. I request Professor Pinaki to present a moment to the speaker.
thank you, Professor George, for your very interesting and insightful talk. So, I think our next speaker is Professor Matthew Barnett from Deakin University. And his topic of presentation is some roles for physical metallurgy in the sustainability of metals. So, Professor Matt.
Thank you very much, Mr. Chairman, and good morning, everybody. So thank you very much to the organisers for the opportunity to spend some time with you this morning. And the topic of my talk is going to be on the subject of sustainability and physical metallurgy. I'll cover topics that I suspect you're familiar with, but I hope that the way I organise my thoughts might be of interest to you and perhaps a little different. I will also mention high entropy alloys. So I understand I'm sandwiched between two talks on the topic, and so I've managed to squeeze some in for you. So physical metallurgy. it concerns itself with the nature, properties, and behavior of metals and alloys, distinct from the older branch of metallurgy, which deals with the reduction of metals from their ores. So when it comes to sustainability, this is an important distinction because a lot of us physical metallurgists can feel that the problem of sustainability and metals is the domain of the people in the other room who are worried about digging the material out of the ground and extracting the metal from it, and it's not so much an issue for ourselves. And by way of illustration, if we just consider the energy required in the process, just the energy required, just one of many facets that might touch upon sustainability, and we look at the primary production and some basic estimates of the energy per kilogram produced, and then compare it to processes that are more of the domain of the physical metallurgist, like melting and rolling, extrusion, heat treatment, and so on, we quickly see that we have orders of magnitude difference. And so it may be easy then for us physical metallurgists to say, oh, look, it certainly is an issue. Look at all the energy they need, and the energy we need is not so much, so perhaps we don't have to worry about it. So, of course, that's not a really advisable way of thinking, perhaps. And there's a very significant facet to how us physical metallurgists can impact on the topic, and it's fairly easily illustrated here. It's because physical metallurgists have a lot to say on alloy choices. As you heard from the previous talk, as you'll hear from the talk after, the physical metallurgist often decides or has a lot to say about which elements we choose to include in our alloys. So when it comes to the embodied energy of primary production, iron, steel is one of the lowest of available elements. But stainless steels, which are very, very widely applied, a very, very common alloy, have a significantly higher level of energy required for their production. That can be understood in very simple terms because of the energy required to extract a chromium, that's in iron-based master alloy, and the energy required for nickel production. So it's our decision as physical metallurgists to put chromium and nickel into steel that accounts for its high energy demand. Now, certain physical metallurgists have preferred to add more manganese rather than nickel, and in so doing create the 200 series of stainless steels, which have, as I mentioned, less nickel, and as a consequence, they require less energy to produce. So in a sense, there's a big role for the physical metallurgist in treating carefully the value that has been placed in extracting the metals from the ground, and we can choose which ones to use, which ones not to use, which ones to use more of, which ones to use less of. So in a roundabout way, I'm trying to argue that there is a very, very important role for physical metallurgists and alloy development in particular on this topic of sustainability. Now, one way of looking at resource use and sustainability that has been talked about for the last 10 or so years is the circular economy. And so it turns out that the circular economy, the idea is to preserve resources in products and in devices. But you can also apply this thinking to alloys. And how do we conserve the resources that alloy designers rely on, okay, the basic elements, in the metals? And so in the circular economy, the field likes to find words that begin with R and use this to describe things that are advisable to use. So to recycle, obviously, is one we're common with. Remanufacture, to repair, refurbish, repurpose, reuse, and so on. So my argument is that this is not a bad way to think as an alloy designer, perhaps. Can we do some of these things when we're thinking of alloys to propose? Can we think of some of these principles of the circular economy? And so I'm going to talk a couple of these today. I've highlighted them in blue. So I'm going to talk to you briefly, this is kind of the plan for my talk, about reducing certain alloying additions which may come with a large environmental footprint. I'm going to talk a little bit about the possibility of designing new alloys that are particularly suitable for making from scrap. And then along the way, I will also mention that one role of the physical metallurgist in this area is designing alloys that can increase the efficiency during the use phase. So let's begin. So to think about sustainability, one has to consider many different topics. And for the physical metallurgist, this is not something we're naturally always comfortable with. And so we spent some time a few years ago in trying to organise some indicators together that might be of use for the alloy designer. And this is what we came up with. So we were seeking a footprint of sorts to associate with an element that we may or may not use in the design of an alloy. And we tried to distill things down into three large areas of application. So economic, social, and environmental. And I'm going to quickly whiz you round the wheel. You don't need to remember it all, because at the end of the day, what I want you to focus on is the little shape in the middle, which is effectively the footprint in this case for iron. So anyway, let's work around. So the first and probably the most subtle of the issues is the one we called NVSR. That's the, well, let's just call it the demand elsewhere in the economy. What we propose to ourselves, that it might not be always advisable for an alloy designer to say, hey, let's use this alloying element that's in big need in batteries and elsewhere in the economy where there is already a high demand. So we think that might be an interesting factor. Of course, supply risk. Supply risk is a very, very important factor from an economic perspective that is affecting, well, prime ministers and presidents talk about it these days. It also played a large role at the end of the Bronze Age for tin supply. Material price, of course, the previous speaker mentioned the importance of high entropy alloys that might find use in reducing their costs, so obviously that's in there. So now we come around to some issues of a more social nature. Labour rights pressures, so if things are produced in an area where labour rights are under high pressure, or human rights, or human health damage. We figured that there's numbers out there, we can consolidate these and let them contribute to a footprint. And then, of course, there's the environmental, and we've chosen to use three. Rock to metal ratio, so how much physical footprint do you make when you extract a certain element from the ground? The amount of water that is used, and then the energy that's embodied, which we've already talked about briefly, which of course scales depending on your local area of energy production with emissions. So there we have a footprint, and so we figured to ourselves it might be interesting, particularly given the interest in high entropy alloys, where we've opened ourselves up the periodic table again and say, let's have a re-look at it all, to consider what the footprints might look like. And so here they are. I don't expect you to digest everything here, but just look at the size and the shape of the coloured regions. Now, the one to pay particular attention to is, wrong one, is, there's a knack to this, evidently, is this guy here. So this is iron, what we saw on the previous slide, or call it steel. It's the smallest footprint of all the footprints available. At least from this snapshot that we took, and there's lots of details underneath this that require justification, but hopefully you can just buy this as a snapshot for now. Steel has the smallest. So even though steel has a massive influence on global emissions, as a per kilogram basis, it has the smallest footprint. So whenever we suggest an alloy that has a possibility of replacing steel, we're going to be up against it from a sustainability perspective, at least from this perspective. So what else could we look at? We could look at cobalt, which has been proposed in a lot of high entropy alloys. It's a very large footprint. Chromium also has a large footprint. And then down over here we have nickel with a slightly different shape, but also fairly large footprint compared to iron. So competing with steel from a sustainability perspective is a big ask. But still, as we heard, there's lots of opportunities out there, particularly in high entropy alloys for unique property suites. And so let's have a think a little bit about a very famous medium entropy alloy that the previous speaker had something to do with early on. So exceptional strength, ductility, toughness, which you've already heard about, so no need to introduce that. This particular alloy has also received considerable interest in the literature. And so from a physical metallurgist, this is a really lovely system. It looks magnificent. But I want to kind of introduce perhaps a few also ugly facts to consider, and you've already saw them on the previous slide. So we're combining 3 elements with considerably large footprints compared to steel. But we thought to ourselves, nevertheless, what could we consider doing about it? And so one of the facets, you heard about twinning, and one of the facets of this alloy, it seems that it has a stacking fault energy that falls in a nice sweet range. It falls in the range of 15 to 25 when you measure it using the separation of partials. And so we would like to consider, well, let's at least look at candidate alloys nearby this that perhaps have a better environmental footprint but maintain the same stacking fault energy. And so for that, we needed a model for stacking fault energy, which turned out not to be so simple. A very nice work, I would think possibly amongst the best, looking at the modelling of stacking fault energy for FCC high entropy alloys. Published a lovely correlation on the right. Unfortunately, for our purposes, which was to look for stacking fault energy in a very tight range, 15 to 25 millijoules per metre squared, having a root mean squared error of 37 is just too great. So I'm not trying to criticise the model, I'm just saying for our purposes, it's insufficient. So quite a high degree of accuracy is needed if we're going to search for a competing alloy with a stacking fault energy in a nice tight range. As an interim measure, we have modified the Olsen-Cohen model, and we've managed to fit it to a training data set of a number of high entropy alloys, medium entropy alloys, and stainless steels. So it crosses those data sets with a root mean squared error of the order of 8. Our testing data set shows that that's reasonably effective. At least it gives us some license to move forward and to try and search, can we look for an alloy nearby that is perhaps a little more smaller in its footprint? And so what came out of this is that perhaps the lowering of cobalt and the adding of silicon might be something advisable. So what we have here are some stacking fault energies for you. So this is the medium entropy alloy, which is the reference. The model says 12, the experiments say 20, so it's within the 8 that we kind of expected. We separate model from predicted here because this was used in the training data set, but predicted that these were not used in the training data set. If you lower the cobalt, which would reduce our footprint, we would increase the stacking fault energy, so we figured that might not be a great path. But if we add silicon on top, we can reduce the stacking fault energy a little further, theoretically, and experimentally we found that was the case. So let's have a quick look at some mechanical properties. Just a short look, and what you want to compare here is the red, which is the kind of the reference, with the green, which is the lowered cobalt to make the footprint a bit smaller, with some adding of silicon to restore some of the lowness of stacking fault energy. And you find that there is a correlation, you can spot it with the other alloy system there as well, that adding silicon, which did have a smaller footprint, may be a way to supplant some cobalt addition. I say maybe because there's many factors that need to be considered here. And I present this more as an example, as an approach that alloy designers can consider taking, where it's not simply the Pareto front of a mechanical property curve or a cost, but there's some other factors that we could put on the Pareto front that might lead us into slightly different directions. Now, we're also in favour of looking carefully at these FCC high entropy alloys, particularly from a sustainability perspective, as a replacement for steels. We think that's a very tough act, but we're also in favour of the possibility, from a sustainability perspective, that it is worth considering continually to look at these high entropy alloys as a possible replacement for high temperature alloys. Now, you already heard about this in the previous talk. Many different compositions are being examined for potential high entropy alloys, particularly refractory containing high entropy alloys as replacement for high temperature applications. From a sustainability perspective, at least from the use of the primary elements, this is a good way forward. So here's a plot that aims to show this. Now, you've got to take your time with this plot because there's lots of things happening. Just go with me. The x-axis is effectively the temperature at which the alloy can be operated at. That's what the x-axis is, the temperature capability of the alloy. On the y-axis, we have the energy that's embodied during primary production. The size of the symbol is how much water is used in that primary production. The colour of the symbol is how much rock is dug out of the ground to create a kilogram of the material. So there's both high entropy alloys on this plot and nickel-based superalloys. For the moment, just look at the nickel-based superalloys. And you can see that as the temperature capability of the alloys have increased, so has their environmental footprint. So as we have made the temperature capability higher, we've also used more water, we've used more energy, and we've made bigger holes in the ground. And on the right, we've just scattered some high entropy alloys. We don't actually know their high temperature capability, so we've plotted them to the right because that's the aspiration. But the main purpose of this is to show you that amongst the high entropy alloys that have been considered for high temperature applications, the symbols are bluer, they're smaller, and they populate the graph at lower embodied energies. So there is conceivably the opportunity to find compositions that might have quite lower footprints than currently, simply from the perspective of primary production. But we know that's not the only thing that matters, because there is what is the impact in an alloy's use phase. That must be considered. And obviously, society, or at least the manufacturer of airlines, have thought it quite justifiable to continue to increase the size of the spots, their darkness, and their height on the plot in the pursuit of more efficient aircraft engines, for instance, or power generating turbines. So one must consider, if we're going to talk about sustainability, what happens during the use phase. So to help us organise our thoughts on this, we can just have a very simple, simply thought experiment. So if you increase the hot zone temperature by 6 degrees, one author said that might give you an efficiency on that gas turbine of 1%. For a 50 megawatt turbine operating for 20,000 hours before you have to replace the blades, the energy you will thus save by increasing by 6 degrees will be about 3 times 10 to the 4 gigajoules. Now, if there is 100 kilograms of turbine blades that are solely responsible for that 6 degrees, okay, there's lots of assumptions here, well then that's about 300 gigajoules per kilogram that you have saved. And on the previous slide, I showed you that the plot only goes up to 3 gigajoules per kilogram. So the saving during use potentially can dwarf any footprint issue from an energy perspective by many orders of magnitude. So one has to consider, well, which you already know, both phases. So here's a way to help organise our thoughts on this. So let's consider the life cycle energy rate, not just from an energy perspective, not just the energy embodied during primary production, but let's consider what happens in the use phase. And a very simple way for a replaceable component is this. With time, you use a material, and during use, you're using up energy. There's an inefficiency of your use. And then when it comes to replacing, of course, you need some more energy to replace, and then you go on and on and on. And this is a very, very simple way to look at it. But it defines a life cycle energy rate, and maybe this is where we should be focusing on when we talk about circular economy, when we talk about alloy development even. So let's unpack it a little more and zoom in on one life cycle. And here's a way we have found that is useful to divide that up, because it's not so simple. So let's just have a look now again. So you start off using your material, and like I said, there's always inefficiencies of use, so you're consuming some sort of energy. Then maybe you choose to repair it. You just insert a little bit of extra energy to give it some more life. Great, good. So then similarly, you will continue to use the product and consume energy. And then the end of a life, things happen. It needs to be returned. So it's either returned to a manufacturer or it's returned to a condition that you can use it again. Whatever, you exert energy in returning it, and hopefully it's not just to landfill. And if you find another application the way the calculation is done here, if you find another application and you supplant something else that has a high embodied energy, then you get a credit for that, what you've supplanted. It's one of the approaches that's used in the life cycle analysis field for considering the accounting. So you can get a credit. So that shows us that it's very good if you have a product at end of life, that you can use it in place of something else that already has a high value or a lot of energy being already expended on. Fairly straightforward, but it's a way to organise the thoughts. And then it comes to the replacement stage. There's a dotted line there, because it may be the same product, but it may not be, so that's why the line's dotted. But then you need primary production, energy for that. There's some energy that might be in a scrap supply, which has a much lower energy embodied in it. And then, of course, you need to manufacture, and then you're off and you're using it again. This has been helpful for us because it showed us lots of different places where physical metallurgy might exert a role. And on the first slide, when I showed you these nice circles of a circular economy, I had one in the middle, which was a nonsense word called resilify. And it's one I made up especially for you, because for physical, and the circular economy people don't talk about it, but from a physical metallurgy perspective, if we can make an alloy last longer, we can make it more resilient, then we effectively extend out that use stage, which then lowers the slope of the life cycle energy rate. So we can see that extending the lifetime is something very, very useful. But for the moment, I promised you I'll talk a little bit about recycling before I finish, and so that's where we'll turn to next. And there are a number of issues with recycling, and I'll just talk about one. It might not be the most important one, but it's certainly an interesting one. Though in some areas it's becoming very important. Because at the end of a life, it's very hard to have materials presented to you as a producer in their pristine condition. Now, there's some very large volumes of alloys that are heavily used, TI-64, 6000 series aluminium, low carbon, so on. There's very large volumes, and so this is working at the moment. But as we develop more alloys, as more recycling comes in, as we develop cleverer components that have more complicated alloys, it's going to be increasingly difficult to obtain at the end of life a pristine alloy ready for its remelting. So this jumble of alloys is going to become an increasing issue if indeed we're going to do more recycling. So I have a few thoughts for you on how we might consider this issue. Now, absolutely the way that's being approached in the field is let's have better sorting, but there's an energy return which it becomes energy inefficient to continue to sort, and then the different processes of extracting when you put the melt together can be flux and all sorts. From a physical metallurgist, I thought let's have a look at what we can do ourselves in our choice of alloys. Can we find alloys that actually might be resilient or robust to variations in their input? And so I presented to you earlier a very simple model for stacking fault energy. So we took that model, and then we just searched, we worked out where the limits of the applicability of the model would be reasonable. So we don't want to extend too far outside our training data set and test data set. And we came up with 2.2 million alloys that we could search. So we did. We searched for stacking fault energies in this narrow range. And then we inspected how dense the space was populated by the alloys that fell within our target range. And so here's one way you can plot this is in this UMAP approach, which is an arbitrary machine learning approach where you collapse multi-dimensional data set into 2 dimensions. You try and preserve the local behavior, but the long distance behavior you lose. But locally, it's a way of looking to see whether there's a high density of alloys giving a same property with similar composition. And so a hot spot on this is a region where you can expect these alloys in that region are likely to be robust to variation for stacking fault energy in their input. So let's have a look at one of these, because I'm running out of time. Let's look at alloy 5. So here's alloy 5 for your viewing pleasure. It's got cobalt, chromium, iron, manganese, nickel, molybdenum, and silicon in it. And the grey of all the alloys, the 2.2 million, it's not the full 2.2 million, because only a subset of those actually gave a stacking fault energy in our favoured range and an FCC structure. So focus on the light blue. What I'm saying is that the light blue is not an alloy, it's a range of alloys grouped around a median alloy that is potentially quite robust to variation in composition. And this is a way to think about alloy development, which I don't think we have used an awful lot of. And it's quite difficult. And it's quite difficult to test this. So I'm proposing to you that there's 990 neighbours within a Euclidean distance of a molar fraction of 0.1 around this composition. Now, to test that is quite difficult because I have to do 990 experiments. So this approach to alloy design means that one has to look at experiments and modelling very closely. And you have to be continually refining the model because you're going to have to trust the model. Of course, you can try some, but in multidimensional space, you can't try everything. So you're having to propose that you do put this into production, and you need to be learning all the time and refining your models so that you can say, yes, this is a composition that might be a benefit. Anyway, so that's a one little thought for you. And I think that now I'm ready to conclude. So I tried to show you that physical metallurgy, well, alloy development, it can reduce the need for elements with a heavy footprint. So that's a contribution that we can make in alloy developers to which elements we propose that we use. Done well, it can foster increased recycling and efficiencies in use, which has occurred for many years already. But I think there is room for an approach which we refine some of the objective functions that we use when we design. And we look at perhaps different Pareto fronts. And we will come up with interesting and quite potentially useful alloy to propose for people to study. And that, Mr. Chairman, is all my talk.
Okay. Thanks, Matt. Thanks for the very interesting talk. And we may just take one quick question, just only one. So maybe. We don't have time, we are running late. Just one quick question.
Hi, Matthew. Very fascinating talk. To come all the way to ask this question from Australia. Raman Singh from Monash University. I have a bit of philosophical question, and I will try to be brief here. Physical metallurgy and physical metallurgists, they